Hi guys, welcome back to Data Every Day. Today we are looking at a data set of medical patient data and trying to predict if a given patient will have a stroke or not. So we have a bunch of features about each patient. At the end we have a stroke event column, which is a 1 if they have a stroke and 0 if not. You can see it is a minority class problem. We do have a very small number of examples in the minority class compared to the majority class. So we are going to probably try to employ some methods to deal with this. So let's hop into the notebook. We're going to use NumPy and pandas for working with the data, and then I was going to use this, but I'm not going to visualize anything today. We are going to use the train test split function, knn imputer, and standard scalar from sklearn for preprocessing, and then these are the models we're going to use. So we're going to train a whole bunch of different classifiers and see which ones perform the best. Then we're going to analyze the results with the accuracy score and F1 score from sklearn.metrics. So let's go ahead and import all this, and I'm going to load in the data using pandas.readcsv. We can grab the file path up here. I'm going to copy the file path, paste it in, and take a look. And here it is. So we have 12 columns. The stroke event is at the end, and then we have a mixture of continuous and categorical features that might contribute to knowing whether or not a patient will have a stroke. So I see there are some missing values in here, so I want to get a little more information with data.info. And it looks like the only column with missing values is the BMI column. So we will deal with those. Let's start preprocessing. We're going to create a function called preprocess inputs. It's going to take in a data frame. It's going to make a copy of the data frame, and for now all it's going to do is return it. We can store the processed version of data down in X, and this way we can modify a fresh copy of the data each time, so we don't have to modify the original version. So the first thing I want to do is drop this ID column, because these are all unique identifiers for each patient, and they don't provide any useful information about whether or not the patient may have a stroke. So drop ID column, and we can do that with df equals df.drop ID from axis 1, which is the column axis, and it's gone. And now there's sort of two things to consider here. One is the missing values. Now because it's a continuous column, there's many ways to impute the missing values. One way might be we could fill it with a mean or some other sort of statistic like that. There are other more advanced methods, and today we're going to do something called the k-nearest neighbors imputation, which basically, after we've processed the other features, we can use the nearest neighbors of a given example to impute the values. So what I mean is, you can consider each example as living somewhere in the input space. And so for a missing value, you'll take that example, find the k nearest neighbors to that example, and then take the average value of the BMI for those examples, and fill it in for that. So we will use that today. Just figured try something different. But the only thing is, before we do the knn imputation, we do have to process all the other features, because it will calculate the distance between features using Euclidean norm, or Euclidean distance. And to do that, we do need them in numeric form. So let's do the encoding first, and then we'll deal with the missing values. So to know about the encoding, we should get a dictionary. It's going to map the column name for every column in X. I'm going to get the column name and the number of the number of unique values in the column. So X sub column dot unique, and then take the length, and that's for every column in X dot columns. Actually, I want just the object columns. So I'm doing X dot select D types object dot columns, and now we can see the number of unique values in each of these object columns. So just the string columns we're looking at. And we have two of them that have only two values, and these are called binary features because they only have two values. Now, binary features are very easy to encode. We're just going to send one of their values to 0 and the other one to 1. So let's do that for ever married. And we can do this with the replace function. We pass in a dictionary with the mapping we'd like. And so this is a yes-no column. So we send no to 0 and yes to 1. And I just want to make sure that the other value in here is no. I would be surprised if it wasn't, but we don't want to make the assumption without checking first. Oh yeah, it is no. No and yes. So we're sending no to 0, yes to 1, and these should all become 1s when we perform this. Oh, sorry, I didn't save it into the column, like that. Alright, and you can see they're all 1s now. So let's do the same thing for residence type, which is our other binary column. So actually we'll just copy this over, and then get residence type, and paste these in. And the mapping is different. We have urban and rural now. So why don't we map rural to 0, urban to 1, and now you'll see that we have 1s and 0s in that column. So binary encoding is done. The other encoding we're going to use is nominal encoding. Nominal encoding, or one-hot encoding, is used when you don't have sort of like, okay, so if you have an ordering between the values, in certain cases you can use that ordering to turn the column into a continuous feature. But if the categories have no ordering between them, we need a different method, which is called one-hot encoding. That's going to take the column. Let's use work type. We take the work type column and we call pandas.getDummies for it, and it sends each unique value in the column to its own column, and a 1 will represent the original value of that example. So we have private for the first example, self-employed for the second. So here we have a 1 for private and a 1 for self-employed. All the rest will be 0s. That's why it's called one-hot. We can include a prefix here. That this can be anything we like. We can make it the same as the column name for convenience, and then it will just add the prefix to the beginning of each column so that we know where these columns are originally coming from. And so I want to use this this function up in a new function called one-hot-encode. And this is going to take in the data frame and the column. It's going to make a copy of the data frame. It's then going to get the dummies, but instead of work type, this will be df subcolumn. And then I want to make the prefix the same as the column name, so I'll pass in column there as well. Then we'll concatenate together with pandas.concat the original data frame and the new dummies columns side by side, so axis 1. And then we will drop the original column from which we created the data for the dummies. So let's return df and use this function in here for our one-hot encoding. So these are our one-hot columns. So all I have to do is say for a column in this list, let me just remove the dictionary aspect of it. For each of those columns, we're going to call one-hot encode, pass in data frame and the column, and then store the result in df. And here we go. So these were all of our original features. You can see the categoricals have been removed and turned into one-hot features. And so now the data is in fully numeric form. So now we can do the KNN imputation. So we're going to use the KNN imputer for this. We could code it up ourselves, but it would just take more time. So I'm using sklearn's KNN imputer. So KNN imputation of missing values. So I'll call it imputer, and that will be the KNN imputer. And this is we're going to fit this only to the train set. So we want to pretend that we don't have access to the test set when we're doing preprocessing. So what I'm going to do is create, we'll do the train test split first. Actually, first I have to split, I split the target off from the rest of the data. So split df into x and y. Y is going to be just the stroke column, because that's what we're trying to predict. And then x is all the rest of the data. So we drop stroke from axis 1, and then we have those two sets of the data. Then we're going to split those into a train and test set using the train test split function from sklearn. I'm going to pass in x and y, specify train size of 0.7, keep shuffle on, and specify random state. So this will shuffle the data, and we include the random state to ensure the shuffle is always made in the same way. And then it will split 70% of the data into the train set and the other 30% into the test set to give us back x train, x test, y train, and y test. And these are the values we want to return from this function. So I'll get them back down here. We could look at x train. So right now, x train is just 70% of the shuffled data with no stroke column. The stroke column is stored in y train. And we're pretty much almost ready to go, except that we still have missing values in the BMI column. xtrain.isNA.sum will reveal that we have 143 missing values in the BMI column. So, this thing, we want to fit it only to the train set. So imputer.fit xtrain. We don't have to worry about ytrain because we know there's no missing values in the target column. Okay, so now we're going to transform both the train set and the test set using the imputer's transform function. And that just means fill in the missing values, but using the fit to the train set. So what this means is the imputer, by fitting, has looked at the input space of the train set, has looked at all the train examples, and sort of memorized where they are in the input space. Then when we call transform, it's going to take an example with a missing value. It's going to look at the input space from the train set, find the nearest neighbors, calculate the mean of their values, and then store it in as the imputed value. So we can use xtrain equals imputer.transform xtrain to perform that. However, this will return a NumPy array, so I'm going to turn it back into a data frame afterwards just so we can have it nicer to look at and get the pandas support. So I'm also going to include that the indices should stay as they were and that the column names should also stay as they were. Alright, and then I'm going to do the same thing for xtest. So we fit only to xtrain, but we transform both xtrain and xtest. Alright, now if we look at the missing values, we have no missing values in the train set, and no missing values in the test set. Alright, so this method, I would say it's probably a better method than just mean imputation. It's a bit more sensible, but there are other methods as well that may offer better performance. So we're going to scale x now. So right now all the columns have different ranges of values, and a lot of models prefer when the columns are all on the same range of values. So that's what scaling will be, and we'll use a standard scaler from sklearn, which will give each column a mean of 0 and a variance of 1. So it will perform a shift in the scale to each column to get all of their distributions in line. And we'll do the same thing we did with the imputer up here. In fact, all I have to do is really copy this, since sklearn makes it easy for us. Just change imputer to scaler. So we fit the scaler only to the train set, and then we transform both the train and test set into the scaled versions of themselves, and then turning them back into data frames afterwards. Alright, and you can see that the columns have been scaled now. If we look at the means of each column, you see they're all very close to 0, and the variances are all very close to 1. Don't worry about this 0. It's due to the one-hot encoding not getting a representative. It's because when you do the train test split, the one-hot encoding may have made it so that there only one 1 in the test set, and now there is nothing in the train set. So there's a variance of 0 because there's only one value. Okay, so let's start training. I think we're completely done with preprocessing. And for the sake of time, I'm just going to copy in this dictionary, which is mapping each model name to the instance of the model. So we have logistic regression, k-nearest neighbors classifier, a decision tree classifier, 2 support vector machines, one with a linear kernel and one with a radial basis function kernel, a neural network, random, and then these are our ensemble methods. We have random forest, gradient boosting, XGBoost, light GBM, and cat boost. And for each name and model in models.items, that means items will return the key value pairs as tuples so that we can iterate through 2 at a time. And we can fit each model to the train set xtrain, ytrain, and print out a little confirmation message that just says each model was trained. And there we go. So before we analyze the results, I would like to point something out. Like I showed you earlier, if we look at the value counts of ytrain, that means what's the class distribution between our labels. You can see we have very few positive labels compared to negative labels. And I'm going to paste this in. It's just going to, basically this is just a print statement that prints out for each model. It's going to print out, it's going to calculate a set of predictions, and then it's going to print out the accuracy value and the F1 score based on those predictions. So the accuracy score is overall how many training examples, test examples did you get correct. You can see here I'm evaluating on the test set. And the F1 score is a much better metric when you're dealing with a class imbalance. As you can see, we have really high accuracies for each model. However, when we look at the F1 score, we have 0 in some of these. Basically what that means is we're completely failing to do the job, because the F1 score looks both at the positive class and at the negative class, and it's a balance of precision and recall. So it's a balance of how well we're doing between classes, but also how well we're doing within classes. So if I quickly import a confusion matrix, I'm not going to display it nicely, but if we import that from sklearn.metrics, and then for example, if I take the first model, so models.values, turn that into a list, take the first value, that would be our logistic regression model. If I call predict on this model for the test set, we'll get a set of predictions. And if I create a confusion matrix to see how these predictions line up with our y-test, you can see this is the negative class. We're predicting all of our predictions in this category, in the negative class, and we don't even have a single prediction in the positive class. So our accuracy is really only, so we have such a high accuracy because the sum of these two, which is this. If let's say we only guess 0, which is literally what we're doing here, we're only guessing 0. We haven't made a single guess in the 1 column. So if we take all those 0 guesses that we made and divide by the total number of examples, we get a 95% accuracy. And you can see we actually don't even have that good of an accuracy on any of our models. So none of these models are even beating the baseline, which is guess 0 all the time. And the F1 score is showing that. The F1 score is completely terrible. F1 score is 0 when either precision or recall is 0, and 1 only when both precision and recall are 0. So it's a much better metric when you're dealing with class imbalance. So I want to see if we can get the F1 score up a little using a method called oversampling. So let's say handling class imbalance with oversampling. Okay. So what this is going to do, we're going to take the positive class and sample with replacement as many times as we need until we have an equal number of negative and positive examples. This will fix the class imbalance, but at the cost of having sort of duplicate data in our positive class. So we can do this. We could use the, there's actually a nice library called imblearn, which has built-in methods for this, but I'll code it up myself. It's not that difficult. Basically, we're going to concatenate xtrain and ytrain back together, because we want to make sure when we're sampling x and y at the same time. So this will just, all this is doing is putting on the stroke column back onto the data frame. And let's call this oversampled data, even though it's not oversampled yet. Alright, then I want to calculate the number of samples to sample. So we can do this way. ytrain.valueCounts, like we saw before. Really what we want is the difference between these two values, because we want to add duplicate values to the positive class until we have enough zeros. So we can take the first value, subtract the second value. That's this minus this, and this will be the number of samples we need to generate. So up here I'm going to say num samples will be this, and then we're going to get our new samples. And this, so let's take oversampled data. Oversampled data looks like this. Right now it's really just a copy of our train set. So let me make sure it's a copy like this. And we can sample this, but I don't want to sample the whole thing, because I just want to sample the 1 values. So we can query it first. We query when does stroke equal 1. Now we'll have only the values where stroke equals 1, and you can see we have 166 of them, which is in line with this. Now we can sample this set of data. We want to sample num samples, different examples. I didn't actually run this. Okay. Cannot. Oh yeah. Okay. So we can't take a larger sample than the population because replace is on false by default. So if we're not replacing after each sample, we'll run out of samples. So we want to change replace equals true, so that we put the sample back each time we sample, and therefore we never run out. And so now we have we have num samples, new examples, and there are duplicates of the original data. But let's grab that and put it here. And I also want to include a random state, so that we can always sample in the same way. Now I want to take oversampled data, and I want to add these new samples to the old data. So pandas.concat oversampled data and new samples. And we're concatenating along axis 0, which is the row axis, so on top of each other. And then we'll sample this thing 100%. So all this is a shuffle. A fraction equals 100% means sample the whole data set without replacement, and include a random state of 1. So we always get the same results. And then when that's done, we'll reset the index, just so that we don't have scrambled indices and duplicate indices. Drop equals true will prevent the old indices from becoming a new column. Alright, so if I run this and take a look at oversampled data now, this should be the new set. So we have more examples, but there's a lot of duplicates in here. If we call drop duplicates, you'll see we're back down to the original set of data. Without that, we have 6,822 examples. And if we look at the value counts of the stroke column, so the class distribution of this, we have the same number in each one. And you can see we've inflated this 166 up to match however many we have in 0. So the last thing to do is to do the split again. We have ytrain oversampled is what I'll call it. And that's going to be the oversampled data, but just the stroke column. And then xtrain oversampled, which is going to be the oversampled data without the stroke column. Alright. I guess I'll just do ytrain oversampled dot value counts. So now let's do this again. So I'm going to overwrite the models, it's fine. I just want to see them here. We're going to train them this time. Oh wait, stop that. We want to train it on xtrain and ytrain oversampled. Didn't seem to have stopped. Okay, there we go. We'll run this again. This time we're training on the oversampled data. Now we'll get the model performance underneath. And we'll see, hopefully, our F1 scores will go up. Now I can't guarantee they'll go up by very much. It really depends on how much information is stored in the features. But we can see maybe there should be an increase in them. Alright, and sure enough, here it is. So we have a 0.25 F1 score, just with our logistic regression, which is far better than anything we had here. Before, our best one, well actually we did have a 0.19 on decision tree. But you can see across the board, every F1 score went up. This is the only one that's really not doing well. Hardly went up at all. Random forest. That was originally a 0.02. It still went up to a 0.04. But you can see that the oversampling did help the performance within classes. So that will sum up today's video. So thank you so much for watching. I hope you enjoyed it. If you did, make sure to subscribe and hit the bell for more content, and leave any comments you have in the section below. I'll see you guys tomorrow. Have a fantastic day.